In module 1, we introduced a brief history of microwave, and then we discussed different microwave frequency bands and also introduced the concept of microwave transmission lines. Then we have seen the lumped element representation of microwave transmission line. Thereafter, we developed the telegrapher's equation. Then we discussed the wave propagation on a transmission line. Then we discussed the lossless line and special cases of lossless terminated lines. So, then we discussed lossy transmission lines and also discussed distortionless line. Thereafter, we introduced a graphical tool which is called Smith chart, and we discussed the basics of Smith charts and how this Smith chart can be utilized in solving transmission line problems. In module 2, we discuss waveguides. We briefly describe the different modes of wave propagation, TEM, TE and TM, and then we discuss how we can have TE and TM mode of propagation in rectangular waveguide, their cutoff frequencies. Next, we discuss TE and TM modes in circular waveguide, and we derive expression for cutoff frequency of such modes in a circular waveguide. And finally, in this module, we discuss the attenuation of waves in rectangular and circular waveguides. In this lecture, we will cover the following contents: a brief introduction to waveguides. This will be followed by discussion on TEM, TE and TM waves. Then we discuss the TE modes in rectangular waveguides. Then we consider the propagation of TM mode in rectangular waveguide. So, waveguide is a metallic tube which is used to guide electromagnetic waves. This is in the most basic form. Of course, there are other form of waveguides also there, like dielectric waveguides, but we will discuss only the hollow metallic waveguides. In waveguide, electric and magnetic fields are confined to space within the guide by the surrounding conducting wall. It is possible to propagate several modes of EM waves within a waveguide. These modes correspond to solution of Maxwell's equation for particular waveguide geometry. Now, let us see the most commonly used form of waveguides, which are rectangular waveguide having a cross section that is rectangular, and circular waveguide having a cross section circular. Please note that we are only showing the outline of the waveguide. In a practical waveguide, these metallic walls will have finite thickness, and these dimensions A and B, or the radius A, what we are showing here, these are the inner dimensions. Now, TEM or transverse electromagnetic wave, it refers to a wave propagation where electric and magnetic fields are transverse to the direction of propagation. For example, if you consider z axis representing the direction of propagation, then for a TEM wave, both Ez and Hz component will be 0. So, the electric and magnetic field will be confined on the xy plane and may have Ex, Ey or Hx Hy component. For example, if we consider a coaxial transmission line, there the propagation mode is TEM. We have E rho component and H phi component, and there is no Ez or Hz component. In the same manner, transverse electric or TE, in that case Ez component is 0 and Hz is not 0. So, in a transverse electric wave or TE wave, Ez component will always be 0. So, electric field is transverse to the direction of propagation, and the axial component of the magnetic field Hz will not be 0. Similarly, in transverse magnetic case, Hz component will be 0, the longitudinal component, and Ez is not equal to 0. Now, while doing the waveguide analysis, we assume that the waveguide boundaries are perfectly conducting and the dielectric region that is enclosed within this metallic boundary, they are perfect dielectric. That means, we are not considering initially any power loss that take place either at the walls of the waveguide or within the dielectric. When we consider practical waveguides, there will be small loss of power both in the metallic walls and within the dielectric, and later we will see how we can estimate such losses. It should be emphasized here that in a hollow waveguide, it is a single conductor geometry, it cannot support a TEM wave. This is because suppose Ez is equal to 0, then in order to support a transverse magnetic field, you require a current in the longitudinal direction. Waveguides being single conductor does not have such current components, and therefore, this type of waveguiding structures cannot support TEM waves. Coaxial cable is a two conductor system, and that is why it can support TEM wave propagation. So, in a metallic waveguide, our solution for the EM waves will be either TE or TM. So, in order to find these solutions, we assume that the fields are time harmonic. That means, time dependence is given of the form e to the power j omega t. And if we consider the source free region within the waveguide, we can write the following Maxwell's equations, curled equations. We further assume that for a wave propagating in the z direction, the z dependence can be written of the form e to the power minus j beta z. So, we have seen when we have this type of z dependence, it gives rise to a wave travelling in the plus z direction. And for such dependence, this derivative del del z essentially results into multiplication by a factor of minus j beta. So, keeping in mind this, if we expand the Maxwell's equations, then we get, considering only the x component from both sides, we have del Ez del y minus del ui del z is equal to minus j omega mu h x, and this del del z can now be replaced by minus j beta as we have discussed, and therefore, when the z dependence is of the form e to the power minus j beta z, we can rewrite this equation of this form del Z del y j beta u y minus j omega mu h x. If you take the other two components h y and h z and their corresponding equations, then we can get these two sets of equations, and if you consider curl of H is equal to j omega epsilon E, then we get this set of equations. Now, the complete set of equations are shown here. From this set of equation, what we can do, now we can see that different field components, how they are related to each other. What we can do, we can express Ex, Ui, Hx and Hy. Please note that these are the transverse components in terms of Ez and Hz, which are the longitudinal components. So, how we can have this relationship? If we consider, for example, the first equation, then we can write Hx is equal to minus 1 by j omega mu del Ez del y minus j beta ui from this equation. And please note that this equation involves Ey, so it has Ez and Ui. Ez is the component which we want to retain, Ui is the component we want to substitute. Now, from this equation we find that this involves Ui, Hx and Hz. So, if we substitute Ui from this equation, we can write Ui of this form 1 by j omega epsilon minus j beta Hx minus del Hz del x. Now, this Ui can be substituted in the first equation of Hx. Once we do that, Hx can be written in the form shown, and once we rearrange the terms, once we expand and rearrange the terms, we can express Hx in terms of Ez and Hz. So, we introduce k square equal to omega square mu epsilon and kc square is equal to k square minus beta square. So, once we introduce, this is the wave number and this is the kc is the cutoff wave number, we will see, and in terms of k and kc, we can now write Hx is equal to j by kc square omega epsilon del Ez del y minus beta del Hz del x. Please note that here we have now been able to express the transverse component Hx in terms of Ez and Hz. If we proceed in the same manner for other field components Hy, Ex and Ui, then we get a set of 4 equations which is shown here. Here we find that Hx, Hy, Ex, Ui all are related to Ez and Hz, and therefore, once we know Ez and Hz, we can always find out the transverse field component Hx Hy Ex Ey. So, solving the field equation within the waveguide region essentially now becomes finding out the solution for Ez and Hz, and depending upon whether Ez is 0 or Hz is 0, we will get the solutions which will be, when Ez is 0 we will get TE solution, when Hz is 0 we will get TM solution. So, one of this component Ez or Hz has to be there to support the transverse field components. Now, suppose we want to write the field variation Hz component, which is a function of x, y and z in this form. So, we can write Hz in terms of small hz x y, a function of transverse coordinate, and multiplied by e to the power minus j beta z. Now, starting from curl of H equal to j omega epsilon E, if we take curl on both sides and then expanding curl of H as minus del square H plus the gradient of divergence of H, and substituting curl of E to be equal to minus j omega mu H, we get a equation of this form. And since we have divergence of H equal to 0, so this equation can be now written as del square H plus k square H equal to 0. So, considering the z component of the magnetic field, we can write del square Hz plus k square Hz is equal to 0, and substituting Hz as a function of, as small hz as a function of x and y and e to the power minus j beta z, then we can write this form of the equation, and writing k square minus beta square equal to kc square, we can write del square del x square plus del square del y square plus kc square is equal to hz x y equal to 0. Now, here kc, which is equal to root k square minus beta square, is called the cutoff wave number. The partial differential equation given by del square del x square plus del square del y square plus kc square hz x y is equal to 0, this can be solved by the method of separation of variables. That is, we assume that hz can be expressed of the form x of x into y of y, and then substituting for hz and then dividing both the sides by x y, we get a equation of this form: 1 by x d square x dx square plus 1 by y d square y dy square plus kc square is equal to 0. Now, we define two separation constants k x and k y, and if we write 1 by x d square x dx square plus k x square equal to 0, in that case we can write this equation of this form d square x dx square plus k square x is equal to 0. Similarly, the other equation can be written as d square y dy square plus ky square y equal to 0, where we find that kc square is equal to kx square plus ky square. So, once we have these equations separated, now these equations, the solution are standard solutions, and therefore, we can now write general solution for Hz. We can write it is a kxx plus b sin kxx into c kyy plus d sin kyy, and these parameters a, b, c and d, these constants are to be evaluated from the boundary condition. So, let us now see what are the boundary conditions in a rectangular waveguide when T modes are being propagated. So, for T modes, we can write Ez equal to 0 and Hx and Hy can be written in this form. Similarly, Ex and Ey component also can be written. Please note that here Ex, Ey, Hx, Hy all expressed in terms of Hz, and Hz we can write a cos kxx plus b sin kxx into c cos kyy plus d sin kyy and e to the power minus j beta z. Now, we have to find out Hz component such that this is the general form of Hz. We have to write Hz in such a way that this tangential electrical component Ex and Ey, they satisfy the boundary condition on the surface of the waveguide, and these boundary conditions can be written as Ex component is 0 for y equal to 0, y equal to b, and Ey component is 0 for x is equal to 0 and x is equal to a. So, once we apply this boundary condition, we have to find Hz which satisfies this boundary condition for Ex and Ey, and the solution of Hz that satisfies this type of boundary condition for Ex and Ey will be of this form: a m n cos m pi x by a cos n pi y by b e to the power minus j beta z. Here we find that kx is actually m pi by a, ky is equal to n pi by b, and it can take values m equal to 0, 1, 2, similarly n is equal to 0, 1, 2, like that, and a m n is a arbitrary amplitude constant. Note that this sign terms in this general equation of Hz, they are dropped so that we can satisfy the boundary condition for Ex and Ey. Now, we can write the propagation constant beta to be equal to root of k square minus k c square, which is k square minus m pi by a whole square minus n pi by b whole square. And this beta becomes a real quantity when k is greater than k c, and when k is greater than k c, we get a propagating wave. Each combination of m and n will give a mode, and each mode has a cutoff frequency. Now, the cutoff frequency for the m nth mode is given by 1 by 2 pi root epsilon mu under root m pi by a whole square plus n pi by b whole square, above which the propagation constant k greater than k c is satisfied. The mode with the lowest cutoff frequency, it is called the dominant mode. Now, if we have a rectangular waveguide for which a is greater than b, then we see that the cutoff frequency, least cutoff frequency will be when m equal to 1, n equal to 0. Similarly, if b is greater than a, in that case the lowest cutoff frequency will be for m is equal to 0, n equal to 1. So, this particular mode TE10, it is having the lowest cutoff frequency, and we will see that it is the dominant mode for a rectangular waveguide. Now, once we substitute m is equal to 1, n is equal to 0 here, we get FC10 to be equal to 1 by 2a root mu epsilon. So, this is the cutoff frequency for the dominant TE10 mode in a rectangular waveguide. Please note that depending upon the dimension a and the values of mu and epsilon for the dielectric media inside the waveguide, for example, if it is air filled waveguide, this will be epsilon naught mu naught, we will get a value of the cutoff frequency FC10, and wave propagation inside such waveguide will only be possible above this cutoff frequency. Also note that m is equal to 0, n is equal to 0 makes all the transverse field components Ex, Ey, Hx and Hy to be 0. So, for the TE10 mode, we can write the field components using the previous equations. Hz to be A10 cos pi x by a e to the power minus j beta z, and Ey minus j omega mu a by pi A10 sin pi x by a e to the power minus j beta z. Please note that we have only Ui component and it will have a sinusoidal distribution over the guide cross section, and it is a function of x. So, we will have the maximum value of Ui x is equal to a by 2, and we see that for x is equal to 0 and x is equal to a, Ui becomes 0. So, this is the boundary condition which is satisfied by Ui, and apart from Hz, the longitudinal magnetic field component, we have another transverse magnetic field component which is given by minus j beta a by pi A10 sin pi x by a e to the power minus j beta z, and Ex, Hy, Ez all are 0. So, here we have only three field components, one electric field component and two magnetic field component. So, we can find out the cutoff wave number. So, Kc becomes pi by a and beta becomes k square minus pi by a whole square. So, at a given operating frequency f, only those modes which are having f greater than f c propagates in a waveguide, and modes, if the operating frequency f is less than f c, these modes they attenuate, because beta becomes imaginary and they attenuate exponentially, and such modes are called evanescent modes. So, even if these modes are excited, they will not propagate, they will eventually die out. And when we have more than one modes propagating in a waveguide, we say that the waveguide is overmoded. So, we have the Ex and Hy component in a for the T mode of propagation can be written in this form, and therefore, the wave impedance ZTE, which is defined as Ex by Hy, and this becomes equal to k eta by beta, where this eta is root mu by epsilon, the intrinsic impedance of the media, dielectric media, and also omega root mu epsilon is equal to k. Now, we also find ZT can be defined as ratio of minus Ey by Hx, which is equal to k eta by beta. Please note that Ex and Hy component, when we consider, it gives the wave which is travelling in the z direction, and Zt is the wave impedance as seen by this wave. Now, we have k is equal to omega root mu epsilon, and which can be written as 2 pi by lambda, and also the cutoff wavelength Kc can be written as 2 pi by lambda c. Now, the wavelength inside the waveguide will be different than the wavelength in the dielectric media at the same operating frequency. So, this can be seen by considering the fact that guide wavelength lambda g inside a waveguide for the propagation constant beta will be given by 2 pi by beta, whereas if we substitute beta in terms of root of k square minus k c square, and therefore, we can write lambda g to be equal to 2 pi by under root 2 pi by lambda whole square minus 2 pi by lambda c whole square, and rearranging these terms we can write lambda by 1 minus lambda by lambda c whole square, and in terms of frequency it can be written as lambda divided by root of 1 minus f c by f whole square, where f c is the cutoff frequency. Now, please note that f c will be less than f for a wave which is propagating within the waveguide, and therefore, 1 minus f c by f whole square, this will become a fraction, and lambda g will be greater than lambda, where lambda is the wavelength in the dielectric media. Further, Vp, the phase velocity, is given by omega by beta, and this is greater than omega by k. Omega by k is the velocity in the dielectric media, which is given by 1 by root mu epsilon. It may be noted that although the phase velocity within a waveguide becomes greater than the velocity of the wave propagation in the dielectric media, and if it is free space, then greater than 1 by root mu epsilon naught, 1 by root mu naught epsilon naught, which is equal to c. So, when we consider actual propagation of energy within the waveguide, it remains less than equal to c. Now, let us come to the TM modes in a rectangular waveguide. For the TM modes, we have Hz, the longitudinal component of the magnetic field, to be 0, only the transverse components of the magnetic fields are present, and Ez, the longitudinal component of the electric field. By our previous argument, we can write in this form Ez x y, a function of x and y, and z dependence is given by e to the power minus j beta z. Now, we have beta is given by root of k square minus k c square, and h x, h y, similarly E x and E y in terms of E z can be expressed in the form shown, and similar to T case, considering z component of the electric field, we can write the wave equation del square E z plus k square E z equal to 0, and substituting E z in terms of the small e z x y, which is the transverse variation due to the transverse coordinate, multiplied by e to the power minus j beta z, we can write del square del x square plus del square del y square plus k c square E z x y equal to 0, and k c as before is the cutoff wave number. Now, as before, this partial differential equation can be solved by the method of separation of variables, assuming E z to be equal to capital X y product of two functions, where this capital X is a function of x and capital Y is a function of y coordinate only, and then substituting E z is equal to x y here and dividing throughout by x y, we get a equation of this form. Once again, we introduce the separation constants k x k y, and we can separate these two equations. So, from these two equations, we can write the z component of electric field as a function of x and y in this form: a cos k x x plus b sin k x x into c cos k y y plus d sin k y y. Now, this ABCD are to be determined from the boundary conditions. And this shows the Ez component, Z component of the electric field in the general form. Now, when it comes to applying boundary condition, here we see that we can directly apply the boundary condition on the Ez component, and the conditions are Ez component, it is 0 for y equal to 0, y equal to b, and similarly Ez is equal to 0 for x is equal to 0 and x is equal to a. So, the solution from the general solution of Ez which satisfy this boundary condition can be obtained as Ez x y z is equal to some b m n sin m pi x by a sin n pi y by b e to the power minus j beta z. Please note that here the k x evaluates to be m pi by a, but we can take the values of m as 1, 2, 3 etcetera, not 0. Similarly, k y is given by n pi by b, and the values of n that we can take again 1, 2, 3 etcetera, not n equal to 0, because if you put either m or n equal to 0, Z becomes 0. B m n here is the arbitrary amplitude constant, and each combination of m and n will give a mode. As in the TE case, we have f c m n, the cutoff frequency is given by 1 by 2 pi root mu epsilon m pi by a whole square plus n pi by b whole square whole under root, and we observe that the lowest order mode that is possible for T m case is T m 1 1. The wave impedance related to the T m modes can be found out in the same manner as in T e. It is E x by h y is equal to minus E y by h x. Now, here in this case it is beta eta by k. Now, to illustrate a particular case of rectangular waveguide, let us consider the example of a very popular rectangular waveguide which is known as WR90. Here WR is waveguide rectangular and 90 stands for 0.9 inch, that means the larger dimension A is 0.9 inch, and therefore, in terms of centimeter A is 2.286 centimeter, and for W190 B is 1.016 centimeter. For such air filled waveguide, the cutoff frequencies for different modes of propagation we can calculate, and we find that the cutoff frequency for TE10 mode is 6.562 gigahertz. Similarly, the next mode is TE20 having a cutoff frequency of 13.123 gigahertz. The next mode is TE01 which is having a cutoff frequency of 14.764 gigahertz. Now, please note that below 6.5617 gigahertz, with this guide dimension, the propagation inside the waveguide is not possible. So, above 6.5617 gigahertz, if we operate the waveguide, we will have TE10 mode launched first, and then if we operate the waveguide above 13.123 gigahertz, then we have both the propagation possible. So, from 6.5617 to 13.123, in this frequency range, the dominant mode TE10 mode only propagates in such waveguide, and therefore, W190 is often used in the X band of frequencies, that means from 8 to 12 gigahertz, when we require single mode propagation. We find that if we compute the cutoff frequencies for TE11 and TM11 for this waveguide, it comes out to be 16.156, and both TE11 and TM11, they have the same cutoff frequency. And when we have this type of a scenario that two modes have the same cutoff frequency, this type of modes are called degenerate modes. For example, here TE11 and TM11 are degenerate modes. So, in this lecture we have studied the TE and TM mode propagation in a rectangular waveguide, and we have derived the mathematical expressions which describe the propagation of such mode. In the next lecture, we will consider the wave propagation in a circular waveguide, and we will consider the TE and TM mode of wave propagation in a circular waveguide, and we will find expression for the cutoff frequencies for TE and TM modes in a circular waveguide.